So I want to just go quickly over the answers to this particular workshop. Some of these, I think, it seemed to me that most of the class was not having much of a problem with A through D, and it was mostly E, but we'll go through them all anyway. So first of all, 1A. So with ln x, the way you do this is you set u equal to ln x and dv equal to dx, then v equals x and du equals dx over x. So that means that the given integral is equal to x ln, it's equal to x ln x minus v du is going to be the integral of x times dx over x. So this equals x ln x minus the integral of dx, which equals x ln x minus x plus c. So that's number one. Let's see. Sorry, 1a. So let's see, 1b. This is the integral from pi over 12 to pi over 4 of x sine 2x dx. So we're going to let u equal x, dv equal sine 2x dx. So v equals negative 1/2 cosine 2x and du equals dx. So we can now evaluate this integral as negative 1/2 x cosine 2x, that's the uv part, and then plus 1/2 integral of cosine 2x dx. It's plus because there's a negative in the v. So that equals negative 1/2 x cosine 2x plus 1/4 sine 2x. So that's the antiderivative, and we're going to let it go from pi over 12 to pi over 4. So that equals negative 1/2 pi over 4 cosine 2x, so that's going to be pi over 2, which is cosine of pi over 2 is 0, and then plus 1/4 sine of pi over 2 is 1. So fortunately this crosses out because that was going to be a little bit of a messy term. And now we want to subtract this expression at pi over 12. So since there's a negative there, we're going to add. So add 1/12 pi over 12, or sorry, 1/2 pi over 12. And cosine of 2 times pi over 12 is cosine of pi over 6, which is root 3 over 2. And then finally we subtract 1/4 sine of pi over 6, which is 1/2. So let's see, so this comes out to 1/4 plus, this is going to be pi over 48. So pi root 3 over 48, and then minus 1/8. So whatever that comes out to, I guess we can say that that's going to be 1/8 minus pi root 3 over 48. So let's see. One C, e to the 3x sine 7x. Okay. 1C, integral of e to the 3x sine 7x dx. There are a couple of, you can actually start this with u equals e to the 3x or u equals sine 7x. I guess I always start it this way, e to the 3x dv equals sine 7x dx. So v equals negative 1/7 cosine of 7x, and du equals 3e to the 3x dx. So the given integral, let's just call this I, just to make it simpler, because it's going to appear in the middle of the problem. So I is equal to negative 1/7 e to the 3x cosine 7x, and then plus, it looks like 3/7 integral of e to the 3x cosine 7x dx. All right, so we need to do this again. U is equal to e to the 3x, dv equals cosine 7x dx, so v equals 1/7 sine of 7x, and du equals, again, 3e to the 3x dx. So this is equal to negative 1/7 e to the 3x cosine 7x plus 3/7, and now we're going to do the whole integration by parts again. So that comes out to 1/7 e to the 3x, and then minus the integral of, minus 3/7 times the integral of e to the 3x sine 7x dx. There we go. So now that gives us I equals negative 1/7 e to the 3x cosine 7x plus 3/49 e to the 3x. Oh, sorry, I forgot in here. That's going to be, I forgot there's a sine 7x in there. E to the 3x sine 7x. And then we have minus 9/49 integral of e to the 3x sine 7x, which is just I itself. So what I have here is 49/49i, because it's just one I, and I'm going to add 9 to that, so that gives me 58/49i equals negative 1/7 e to the 3x cosine 7x plus 3/49 e to the 3x sine 7x, and I simply multiply everything by 49/58, giving me I equals, let's see, negative 1/7 times 49/58 cosine 7x, e to the 3x cosine 7x, and then plus 3/49 times 49/58 e to the 3x sine 7x plus c. We can simplify this a bit. This is going to become, let's see, negative 7/58. And this is going to become 3/58. So that's the answer there. So let's see what else is there. Arctan of x. This is actually not a very difficult problem. So integral of arctan x dx. This comes out to u equals arctan of x, dv equals dx, v equals x, du equals dx over 1 plus x squared. So that is, this is going to work very much like the ln problem. So this is equal to, let's see, x arctan x, that's the uv, and then minus the integral of x dx over 1 plus x squared, that's the v du. So here we can actually do this part by u substitution, so I'm going to reuse the u term. So that's u equals 1 plus x squared, du equals 2x dx, so x dx equals 1/2 du. So this equals x arctan x minus integral of 1/2 du over u, and that's going to equal x arctan x minus 1/2 ln of u, which equals x arctan x minus 1/2 ln 1 plus x squared plus c. There we go. And finally, we have the one that I think everybody was somewhat confused about. 1e. This was the integral of sine to the fourth x dx. So the way that you do this is we're going to let u equal sine cubed of x and dv, or sorry, not dx, there's no dx there, dv equals sine x dx. So du is equal to 3 sine squared x cosine x dx, and v equals negative cosine x dx. So let's actually let that be. Actually, I don't want to do that. So let's see. The integral of sine to the fourth x dx is equal to, it's going to be negative sine cubed x cosine x, that's the uv part, and then since we have a minus in the v and positive du, we're going to add, so that's going to be integral of 3 integral sine squared x cosine x times cosine x is cosine squared x, and we do have a dx there. So here we use negative sine cubed x cosine x plus 3 integral of, I want to convert the cosine into sine, so this is going to be sine squared x 1 minus cosine squared x dx. That gives us negative sine cubed x cosine x plus 3 integral of sine squared x dx minus 3 integral of, sorry, this I meant to write sine here, because cosine squared becomes 1 minus sine squared, so that becomes 3 integral of sine to the fourth x dx. So this is where the, this is where the sine to the fourth actually appears on both sides of the equation. So that gives, if I add 3 of that to the 1 on this side of the equation, I get 4 integral of sine to the fourth x dx is equal to negative sine cubed x cosine x plus 3 integral of sine squared x dx. Now what I can do before I do anything else is I can simply find out what the integral of sine squared x is. There are a couple of ways that you can do this. I personally find it easier to do by integration by parts, so I'm just going to do it again. Let's just evaluate and do it in a different color. Sine squared x dx, we're just going to write u equals sine x, dv equals sine x dx, v equals negative cosine x, du equals cosine x dx. So that gives us that the integral of sine squared x dx equals negative sine x cosine x, and then plus, we have cosine x and cosine x in the v and du, so that just becomes plus integral of cosine squared x dx, which equals, this equals negative sine x cosine x plus the integral of 1 minus sine squared x dx. So that equals, so let's see, that gives us negative sine x cosine x plus the integral of 1 is just x, and then we have minus the integral of sine squared x dx. I move this negative sine squared x over to the other side of the equation, giving me 2 integral of sine squared x dx equals negative sine x cosine x plus x. So I have the integral of sine squared x dx equals negative 1/2 sine x cosine x plus 1/2 x. So I now have the integral of sine squared x dx by integration by parts. Let's just bring this equation down here. So 4 sine to the fourth x dx, I won't read the whole thing. This is equal to negative sine cubed x cosine x plus 3 times this expression. So this is the expression for sine squared x. So that's going to be, let's see, that's going to end up being minus 3 halves sine x cosine x, and then plus 3 halves x is equal to 4 integral of sine to the fourth x dx. So now I just divide everything by 4, and I get negative 1/4 sine cubed x cosine x minus 3/8 sine x cosine x plus 3/8 x. That should be correct. Okay, so that's how you do 1e. All right, let's see. So use integration by parts to write cosecant to the sixth 2x in terms of cosecant to the fourth 2x, and start by explaining in 1 to 2 sentences why u equals cosecant to the fifth 2x is a terrible choice. And I realized there was one version of this where I had said explain why cosecant to the fifth x is a terrible choice. It is a terrible choice, but it's so terrible that it's hard to explain, so I'm not even going to bother explaining that. The issue is that if I were to choose u equals cosecant to the fifth 2x, then I would have dv is equal to cosecant 2x as the choice of dv. Now, it's not that there isn't a way to find the antiderivative of cosecant 2x. We could do it by the same technique that we used to find the antiderivative of secant. It's just that what you're going to get is you're going to get ln of something plus something else, and that's not really going to be very useful, because then du is going to be 5 cosecant to the fourth 2x times cosecant 2x cotangent 2x times 2 times negative 1 times dx, and then you're going to have to multiply that by this expression for v. So basically the point is that you're going to end up with natural log of a sum of two trig functions times 5 times a bunch of other trig functions, and it's just not going to be helpful, because you're going to end up with this u dv that you can't integrate if you do that. So the idea is that you want to choose, the simple explanation here is that you want to choose dv to be something that's going to be really, really easy to integrate and give you a nice clean antiderivative. So the better choice here is going to be cosecant to the fourth 2x, dv equals cosecant squared 2x dx. And by the way, I watched a couple of you do this in the workshop, and some of you sort of ignored this. You ignored the integration by parts part, and you said, oh, I can just do this by using the trig identities. Yes, you can. I really should have made this an odd number so that wouldn't work, but I didn't. So you still have to follow the instructions. So here you have du is equal to 4, actually it's going to be negative, so negative 4 cosecant cubed 2x cosecant 2x cotangent 2x dx, and v is going to equal negative 1/2 cotangent 2x. Okay. So, I actually forgot one thing here. I forgot the chain rule step. I have to multiply that by 2 dx there. Okay, so what we're going to have here is we have integral of cosecant to the sixth 2x is equal to uv, which will be negative 1/2 cosecant to the fourth 2x cotangent 2x, and then we've got two negatives, so we can still keep the negative here. So let's see, that's negative 4 times 2 is 8 times negative 1/2, which is negative 4. So that's going to be minus 4. Yeah, there we go. Minus 4 integral of, let's see, let's combine terms here. We're going to have cosecant cubed times cosecant is cosecant to the 4th 2x. And then we have 2 powers of cotangent, so that's going to be cotangent squared 2x dx, like that. And now what we're going to do is we're going to rewrite this using identities. And let's see. Yes. So, okay, so we're going to write this using identities, and this becomes now minus 4 integral of cosecant to the 4th 2x, and this is going to be cosecant squared 2x minus 1 dx. So this equals negative 1/2 cosecant to the 4th 2x cotangent 2x minus, this is going to be 4 integral of cosecant to the 4th 2x, and then plus 4 integral of cosecant to the 4th 2x dx. Sorry, there should be a dx in there. So now I can add 4 times cosecant to the 4th 2x to the other side of the equation. That gives me 5 integral of cosecant to the 6th 2x equals negative 1/2 cosecant to the 4th 2x cotangent 2x minus 4 integral of cosecant to the 4th 2x dx. I've moved this, or sorry, this was, sorry, let me back up for a minute. I want to do this correctly. This should be the 6th 2x. There we go. That's now correct. Okay, so this is negative 1/2 cosecant to the 4th 2x cotangent 2x, and I'm going to keep the 4th on one side, so that's plus 4 integral of cosecant to the 4th 2x dx. This is what gets moved over, so now I get this term gets moved over to the other side, so that's going to be 5 integral cosecant to the 6th 2x dx, like that. And now I can finish the problem. Like this. So cosecant to the 6th 2x dx equals negative 1/10 cosecant to the 4th 2x cotangent 2x plus 4/5 integral of cosecant to the 4th 2x dx. And that is the integral of cosecant to the 6th 2x rewritten in terms of integral of cosecant to the 4th 2x. And by the way, of course, for reasons that have been explained in the lecture, you do not need a plus c at the end of this, because the indefinite integral here already includes its own plus c. Okay, so now let's just put in here the solution to this. So this was an issue that many of you seem to have a lot of trouble with, because I think that you had trouble understanding what I was asking. So let's unpack what the problem actually says. We've learned that rewriting sine to the nx as sine n to the n minus 1x sine x is only useful when n is odd. There's probably something a little bit missing here, which is that it does work when you use integration by parts, but that's not what I'm talking about. The point is the way it's described in the lectures and in the book. What we're saying is that if we want to do this by u substitution, that was the technique that was really being given, it's only useful when n is odd. So what I wanted you to do was to try to use that try to use this particular technique that's being described, the one where we peel off a factor of sine q, peel off a factor of sine x, and then use the process that we would normally use for an odd n until you can't go any further. So we're going to rewrite sine to the fourth x dx as the integral of sine cubed x sine x dx. So the idea is that if we had started with an odd n, in other words, if I had started with something like sine to the fifth x dx, I could have rewritten this as sine to the fourth x sine x dx, and I would have said, let's let this be some factor of du. So in this case, what we would have done is we would have said that sine is going to be part of the du, and therefore we want to rewrite everything else in terms of cosine. That's the technique that I was referring to. So this is going to be u equals cosine x, du equals negative sine x dx. So negative du equals sine x dx. So this is going to be negative du, and what I then have to do is I would have to rewrite this integral using the identity cosine squared x, using the identity sine squared x equals 1 minus cosine squared x. So what I have to do is rewrite this as sine squared x to the 3 halves sine x dx, and this is going to be then integral of then this is going to be the integral of 1 minus cosine squared x to the 3 halves sine x dx. So now this is going to be negative du, and then this is going to be 1 minus u squared to the 3 halves. So let's suppose that I had actually done that. Let's suppose that I now had this integral of 1 minus u squared to the 3 halves times negative du, which I can then even rewrite this way. 1 minus u squared to the 3 halves du. So how do you do this? Well, we now know, even though we didn't know it at the time that the problem was given, we now know that you could do this by trig substitution, but that's really, really messy. The idea is that you want to use this technique only when you start with an odd power of sine. If I had started with an odd power of sine, then what I could have done, like let's suppose that I started with sine to the fifth x dx, then I could have rewritten this as sine to the fourth x sine x dx, with again the same u equals cosine x, du equals negative sine x, and then I'd rewrite this as the integral of sine squared x squared sine x dx, which would be rewritten as 1 minus cosine squared x squared sine x dx, which can now be rewritten as 1 minus u squared squared du with a negative sign in front of it. So this at least could be evaluated, because we could take this expression and we could actually multiply it out, as we did in one of the examples. This became 1 minus 2u squared plus u to the fourth. But there's no way to do that here. We don't really know how to take this expression and expand it so that we'd be able to evaluate it by any reasonable method. The point of this problem was just to get you to understand why it is that the rule for evaluating an integral like sine to the fifth x relies on having at least one odd power of sine and cosine. It's just that it doesn't make it any easier, specifically because you get this fractional exponent. If you start with an even power, reduce it to an odd power like I've done here, and then try to go from there, it doesn't work. So yes, you can, if you break it up this way and then do integration by parts, but that's not the technique that we're really looking at. So that was the process I wanted you to go through and explain, is to understand why why the standard technique, the first technique that we learned for doing this problem, really only works if you start with an odd power.